we're going to talk a little bit now about data, and this is one of my favorite subjects, right? Because as an analyst, you can do lots with data. You can a lot of times pull any story out of data that you want to, and so we got to be really careful about that sort of thing, especially if somebody's trying to prove something with a data set. And so statistics, of course, can be a little bit challenging sometimes. So a couple of things I'm going to talk about. One is the fallacy of the 30-day IP, or peak rate. I prepared this in Excel a few years back, before we had some of the really cool tools we have out there on the market now. You don't have to do this stuff in Excel anymore. There's software out there where you can generate these sorts of plots really nicely. But what I did is I took every producing oil well in Alberta since 1987, and I just put them all on a big cross plot. And what I wanted to see was, is there any correlation between what a well produces over its first calendar month and what it's going to produce over the first 5 years? What I like about this is that there's zero subjectivity, right? This is hard data. I don't have to interpret a decline curve or anything, or forecast. And I was a little bit discouraged and not too happy with the fact that I didn't really see any sort of trend here at all. But we routinely, as an industry, put a lot of emphasis, and this is especially true in the investment community, on a first 30 days IP, okay, for what the well's produced, or its peak rate. It's called different things, but what a well is capable of in the first 30 days. And it's not surprising that we do that. I mean, we want to find out right away. We want the first information that becomes available, right? Like, timing is key. We want to know as soon as possible how good of a well this is. So, why I started asking myself, why is this the case? Why don't we see a better trend here? Well, there's lots of reasons for that. During the first month, there's usually a lot of operational discrepancies. Like, some operators will have the well shut in. Sometimes wells will be flowed back on choke. Sometimes they'll be flowed to open conditions. So the true reservoir capability is often masked during the first month of production. So we're not getting a clear picture of what that well is really going to be capable of doing. What if we, instead of looking at the first 30 days, we look at the first 3 calendar months, so the first 90 days of production? Well, we get a little bit better. You can see the trend is starting to emerge, but it's still not good. Even after 90 days, you still have these masked, reservoir performance is really masked. There's all these other influences that are taking hold. And our correlation is, less than 0.5, so it's not great. My buddies at Visage, which is now Verdazzo, were kind enough to point out to me yesterday, and I didn't even realize this, that a lot of what's reported in the industry is actually a producing time IP. So there's a subtlety here that's, in my opinion anyways, very, very important. When you talk about a 30-day IP, is it a calendar IP, or is it the first 30 days producing time? Those are very different metrics, right? So make sure you understand what's being reported. And neither of them are perfect metrics. Neither of them are going to be perfectly indicative of what's going to happen in the future. So a producing time IP has its problems as well, because as you can see, these two wells actually have exactly the same 30-day producing IP, even though when you look at their production profiles, it looks like the red well is actually quite a bit better. So I gave it some thought, and the way I kind of look at this is a calendar time IP is always going to be biased towards wells with low downtime or high drawdown. Whereas a producing time initial production is going to be biased towards wells with high downtime and or low drawdown. So if I'm a company that has a well that I've got a lot of shut-ins during the first few months of production, and I want to really show investors that I've got good wells, I'm going to use a producing time IP. On the other hand, if I've got a well that's got I flow it back, on no choke, or flow it back to open conditions and don't shut it in very much, I'm going to use the other one, right? So just be aware, you can mold the data to really influence and show different things. So ask those questions. The Verdazzo guys did some really good work here, much more comprehensive than what I did with my study of what is a good predictor, and they used EURs. So the idea here is correlating early performance indicators to long-term EUR. And they did various different study areas, including Montney, Cardium, Viking, Bakken. You can find this on their blog. I'm not going to get into a lot of details, but basically, green is good, orange is not great, red is terrible, gray is abysmal in terms of correlations. So where you really start to see greens across the board, you're getting into some pretty high numbers in terms of IPs, right? You got to let that well flow for 6 months, maybe even a year before you're getting greens across the board. It takes a while. Here's my example. This is where we get into the rate transient analysis. So in this particular case, what you're going to find is neither producing time IP or calendar time IP is going to be a good indicator of long-term performance because we're missing a key piece of information, and that's flowing pressure. When you look at just the pure production performance over the first 3 or 4 months, anybody that looks at this is going to say that well 1, is better, empirically is better, whether it's producing or calendar time. But when we model this on an RTA plot, so this is our standard specialized linear flow plot, we get a different picture. Okay? And for those of you that haven't seen these plots before, the flatter slope indicates the better well. Okay? That's what we're looking for, is the slope of that line. So in actuality, well 2 is a better well, is going to be a better performer, which is surprising because when we look at the production profile, it certainly doesn't look like that. So that's the conclusion we came to when we looked at it in RTA. And then, of course, we can go forward with a production forecast, long-term production forecast. We ended up updating that production history a little bit later, and sure enough, the red well was a late starter. It came into its own a little bit later on. It had a much lower decline rate than the purple well did, and early predictions seemed to be on track and showed well 2 to be a better performer. This is a fairly severe case. You don't see cases that are that misleading at the beginning, but there are certainly lots of other examples where this happens. Let me switch gears here and talk a little bit about false causality. This is a really favorite topic of mine because this is another area where you can really look at a large data set and easily be misled. False causality, very simple. It's the belief that correlation proves causation, right? So if you see A is related to B, B must have caused A. Let me give you a couple of real-world examples. I love these ones because this is a real-life thing. Maybe we've all been there. Maybe I've been there. Sleeping with one shoes on is strongly correlated with waking up with a headache. Therefore, sleeping with your shoes on causes headaches, right? Well, they're correlated, so one must cause the other. Because we all understand that that's nonsense. We know that there's a hidden variable in there somewhere, and we all know what that hidden variable is. Here's another example. As ice cream sales increase, the rate of drowning deaths increased sharply. Therefore, ice cream consumption causes drowning. Well, that's ridiculous. Obviously, that's not the case. But there's a lot more ice cream sales in the summer, and people are doing a lot more swimming in the summer. So that's the hidden variable. So these are obvious ones. Where we don't see that being so much obvious is when we start to look at oil field data. But the same sort of thing happens with oil field data. And I'll give you a couple of examples. Here's one that and I'm not going to call out anybody or name names, but this is one that we've seen. I have a lot of experience working in the Eagle Ford, and we had access to a very large, rich database there. So we had a pretty good idea of what was going on in this area. And there was a study done that showed a relationship between peak rate, which you already know I have an issue with, and proppant type that was used in the well. So the study looked something like this. And proppant X was held up on a pedestal as the thing that's driving production in the Eagle Ford. And so everybody's like, great, let's buy all the proppant X that we possibly can because that's driving performance in the Eagle Ford. What they didn't know, and what I knew because I had access to all of this data, is that proppant X was used by a single operator. It was sort of very interesting. There was only one operator that was using this proppant. And I don't know why. Nobody else was using it, but they were using it. And it turns out they also had a really good land position in the Eagle Ford This operator is also known for flowing wells back unchoked. So there's actually two hidden variables here, right? There's one where it's like, we're flowing our well back unchoked, so we're going to get a better 30-day IP anyways, because we're not using a choke. And also, there's a hidden variable of this operator happened to have a really good spot in that part of the Eagle Ford. So they are able to maximize their production. So, we're not drawing the conclusion that proppant X is not important. All we're saying is that there's other things to consider there. Just because two variables are correlated does not mean that one causes the other. Here's another example. Frac fluid additive X is correlated to better well performance. Therefore, using additive X will result in better well performance. I don't have a plot for this one, but the reservoir engineering insight that goes with this is that frac fluid additive X was only used in wells. It was affiliated with a particular oil field service company that happened to be the company that had the most horsepower and was pumping the biggest jobs in the Permian. Again, it's not to say that frac fluid additive X doesn't have value, but it's piggybacking on another much more important variable and sort of taking credit for that, so to speak. So this sort of thing happens all the time. You'll see examples of it, and some are harder to pick out than others. I gave you a couple that are, I think, a little more obvious examples. So how do we actually do this properly, right? So how would we conduct a study that can really understand what well performance is telling us? Well, this is my area of expertise, so this is really exciting to me. I can go and look at this and actually answer this question a little more objectively. And of course, we all know there are many different things that drive well performance. I've listed a few of them here, but this isn't an exhaustive list. There's other things. So there's items that you could relate to operations. There's items that you could relate to reservoir and fluid properties. There's items that you could relate to the completion and the wellbore. All of these are going to influence well performance. Proppant type is on that list, but it's just one of many items. Okay, so if we're interested in seeing what the impact of proppant type is, let's do it a little more objectively. So we did that, and we generate these sorts of plots in my group all the time. These are sensitivity analyses based on reservoir models that are generated using RTA or simulation. And to do a plot to generate something like this, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, whatever it is, variables, and we have to do 3 different corner cases. So that this is the result of running, 36 models, for example. Okay, so it takes a little bit of prep work to generate something like this, but it can really give you a good sense of what's driving performance. So this is a sensitivity analysis. The low side is going to be if I take that variable on the low side of its sensitivity, what's the EUR going to be? And the high side is up here. And the objective function that you're using matters as well. In this case, we were measuring this against 1 year oil produced. If you did the same plot against 5-year oil produced, you'd get your bars would be different and maybe be in a different order. So what are we trying to say here? Well, one thing I'm going to say is that we always look at like the top 3 or 4 bars. Those are the ones that are driving that 1 year oil produced number the most, right? And on that list, probably not too surprising, we have permeability, thickness, fracture length, number of stages. And this is specifically for this area of the Eagle Ford, which we have a lot of background data. So I believe that. We have some good data to support that. What about proppant? Where does it come in? Well, proppant really has an impact on fracture conductivity. And frac conductivity, at least in this area, doesn't seem to be a driver of performance. The bar is very, very small, so it doesn't seem to have very much of an impact. So that's really the result that we found, which makes me really question the conclusions of a study that would say that proppant is driving performance. So false causality, beware of sweeping conclusions, usually based on two-dimensional correlations. There are very few good, reliable two-dimensional correlations in oil field data. There's usually so many multiple parameters that influence performance and influence your objective function that it's hard to find any sort of correlations. You have to do more like multivariate analysis to really understand what's going on. So the vast majority of well performance variance results from differences in rock and reservoir fluids. I say that because I've got my two geologists are here, so I want to make sure the rocks matter. They're important. So reservoir engineering insight will help us find the true underlying performance drivers that are specific to our play of interest. So we can do that on specific areas that we're interested in. Switch gears again here. Let's talk a little bit about statistics 101. Again, I'm not a statistician by any stretch, but as a petroleum engineer, I have to use, and it's becoming more and more important for us as petroleum engineers to use large data sets and try and find information, pull useful information out of them. And maybe perhaps more importantly, critically analyze and understand reports that other people have written using large data sets, because everybody's getting into this big data now. So I'm going to talk about a couple of different things that I think are important, pretty basic stuff, but I think it has an impact. And one is mean versus median. What you're looking at here is a cumulative distribution plot of EURs. So these EURs are interpreted just using standard decline curve analysis. This is from a study that we did for a company a few months back in the Bone Spring Formation in Lee County, New Mexico. And the idea here is, well, there's quite a discrepancy between the EUR from the mean, or the median, and the mean, right? Mean is just average, median is P50. So what do we do about that? What do those numbers mean? Well, here's another example. These are a collection of tight gas wells from the Jonah Field in Wyoming. And this group, that's the well count, producing well count right here. It's around 17. I'm not even going to get into things like survivor bias. That's another thing that we need to consider with type curve analysis. But I made sure I chose a constant well count to generate my curves. So I've got a P50 and I've got a mean. Again, pretty big difference, right? There's a 25% difference between the average and the P50. And that's not even really an extreme example. That collection of wells is decently sort of clustered. I tried to choose sort of an average collection of wells. So here's what I think, okay? Median is going to be a better indicator of how a new well is going to perform when you drill a new well. The reason for that is simple. Median is your P50. So 50% of your samples are worse than that, 50% of your samples are better than that. So if you're going to drill a new well, chances are that's exactly your 50% line. The problem with mean or average is it's going to be influenced by outliers, right? So if you drill a really good boomer well, the average is going to be pulled up from that. And guess what? Oil field production samples and well samples are almost always log distributed. That means they have these outliers on the high side that are going to pull that average up. So if you're an oil and gas company and you have the choice in your investor slide deck of promoting a type curve that's based on an average or a P50, which one are you going to pick? Right? So just be aware that those are sometimes, and there's lots of other reasons that I've already talked about how type curves can be inflated and perhaps provide a falsely inflated version of what reserves or reserve potential might be. But this is another way that might happen. So E&Ps that use type curves based on mean are likely to overstate the value of undrilled acreage, especially if they have small drilling programs, right? So the problem of mean versus medium starts to go away for very large data samples. If you have a really, really large drilling program, it's not going to be as much of a problem. But if you're working with just a few wells as your sample, and you're going to drill only tens of wells rather than hundreds of wells, this is going to be a real issue. And then just another comment at the bottom, type well curves created using limited statistical samples are unreliable. It sounds kind of gloom and doom, but we just need to be aware of the uncertainty, that's all.